Good evening, sir.
Right. Hi, good evening. Nice having you here. Yeah, sorry for the delay. I'm just trying to give a little time for others to join us. At least by waiting the next 2 to 3 minutes, if no one comes, I'll just begin with what we have to do. Yeah, all right. Good evening, guys. Nice having you on here. So without further ado, I'll begin with the first we have for today. We'll be talking about data modeling. So let me just start by sharing my screen here. So, yesterday, we dealt with introducing the topics like quick revision from our first class, which was on Thursday. And then we talked about the importance of data modeling in machine learning and why model data and machine learning. We actually skipped this area, what our regression type, because we didn't really need it at the moment. So talked about the steps involved in modeling data, which is we followed in form of a checklist. Where we started by preparing the data set, what we did in our practical meeting, where we first had an overview of the data sets. We looked at the unique, the values that needed encoding, those that needed to be filled, like that were not complete, to say those that were not complete. That's to be more precise, the item weights and the outlet size. These were the two future columns that needed to be filled. So we filled the missing values, and we didn't do any form of future selection because of we couldn't say if there was a particular future column that needed to be dropped also. Then we did the future engineering. This was where we converted most of the categorical columns now to, well, we didn't convert it in the last class, but we talked about how it could be converted, making use of the various encoders. That's the label encoder, the ordinary encoder, the one hot encoder. So we talked about all of this. Then we also talked about future scaling, which was the last thing we tried to do in the class from yesterday. So in this class, what we'll be taking today will be model selection. So I want to first start by introducing what the act of model selection is really all about. I wrote on it in a, I wrote an article on model selection that I really like you guys to check out, where I tried to define what model selection is really all about, why we actually made it in the whole context. You know that we already started. Data modeling stuff is kind of like a step-to-step process where, okay, we started with the data cleaning and the this and the that. But our overall objective was that at the end of this, we want to predict, all right? And we use the term predict here because we can never really be precise, but want to predict, get a close estimate to what the reality of a value is that making use of the data sets now. So The major step in doing this would be the approach which we use, which is the model now. And there are different kind of model in the machine learning space. So by the time model here, what I mean, because I'm very good in making of the concept model, but what I really mean are the machine learning algorithms, that are necessary to make the predictions now. And what this machine learning algorithms really do is that they are not actually learning. They are not learning, so to say, but they are actually learning patterns that exist in the data. So let me just, what I'll just try and do now is I want to try and give a quick example of what this data might be implying. We know that from our data set, what we have now is various features. So given the item identifier, the item weight, the item part content, the item visibility, the item type, the item MPR, MRP rather, the item MRP, the outlet identifier, the outlet establishment, the outlet size, and all of these things. That is picking all of these values now. We are trying to ask the machine learning model, like, can you find the exact relationship that exists, the exact pattern now that exists between these, adding up these features together that got this. So basically what we are doing is we are trying to create a math function, and the math function that we're trying to create is something like this. Let me just quickly run this and restart and run this notebook so I don't have to stop around this area because it's an error. And you would have noticed that I made I adjusted the notebook a bit. So I adjusted the notebook a bit to because of the error that we have here. So just to explain what's really happened and why it's happening. So you guys will check that I uploaded the link to the GitHub. That was it happening. So this is where we are at. This is where we were as of yesterday. So as I was saying, the model tried to create a function now. And if you are familiar with linear algebra, you know that it does something like saying, okay, f of x equals y, where x here now is our training data, which is all of this, and y is our is our target variable. So what our model tries to do is it tries to look for what the function of x is, and by the function of x, that is what particular formula does this specific features in x have a formula. That is, it looks okay if we have an NPR of this plus this and this. I'm just giving an example. I'm not really saying that it's good, but if we have that and that, how do we know that this should be the resulting from this thing? So f of x is the formula that our model is trying to predict. And once it gets that formula, it will be able to predict future y, making of that formula, taking x as input. So all of this stuff are just mathematical terminologies. And all of these are just mathematical terminologies that I just wanted to actually state out before we even start going to far. And I'm very sure you guys are familiar with the concept of regression. So just to to clear the space about what regression data analysis is really all about. A regression analysis is always something like this, where we have this series of data points now, and we are trying to ask our model to fit a line through that data. Now, these data points that we see here is like the values. Now, where x, and it's not always like this because this is a two-dimensional space now. but just for a relatively simple way to understand, an intuitive way of understanding this thing, what our model is trying to do is it tries to look at what the target value is in relation to the prediction and tries to fit a line through it in such a way that if it was to make a prediction, say something of this point now, let's predict the exact same value here, which will be here, it will be close and not so far from the truth. But that is why I said a machine learning model does it just makes an attempt to predict what the outcome should be. It's not actually very perfect, so to say. So I'm done with that. Before we go into what model selection, how to select a model, the first thing we need to do is talk about the data sets. Why do we, like, if we were to select a model from the data set, we need to perform a task of splitting the data set. And why do we need to split the data set? Now, the thing is, if you wanted to write an exam in school, or sorry, not write an exam per se, if you wanted to learn a course in school, after teaching you the course, they do some things for you. They give you like a test question, and that test question are actually questions from the materials we were given in the class, but not always going to be direct in such a way that it doesn't come in a manner that was the same way you were taught. It doesn't come in that same manner in which you were taught. The test tries to check your intuitive understanding of what you learned during the class. And then you move further to the exam, which is a more robust way of testing, whether you've actually perfected what you learned during the period that you were in class. Now, when we split our data set into the various, when we perform data splitting on our data set, what we are trying to do is, okay, we want to train our model, say, create this now for the model, this particular image that we are seeing now for the model. We want to have a set of data here now that will be what we call the training data, which is what was used to train the model. We want to have that training data, have the model learn on the training data. Then when we are doing the testing, we will now have another series of data points, which will not be this passive, but the line, this particular line that we have right here, we remove. So this particular line we have here will remove. So when the new data point appears, it's going to be something different. It's going to be something different, but at the end, based on the line from the previous, from the training process rather, the model will be able to guess what the values of the test data should be, even though it won't be so precise. And we have a way of measuring the precision of the model now for regression tasks. This is called actually, there are very two common modes of measuring it. There is the mean absolute error, and there is the mean squared error. And what these two terminology just means that, okay, you know that the best way to know if this model is performing optimally is to check the distance between this point and this line, this point and this line, this point and this line. It does that for all of the points and the line. Then it finds the mean of that distance. That's for the MAE, which is the mean absolute error. And I did, I believe I wrote a lot about the mean absolute error. So just in case if you don't get all that I say if you don't understand me perfectly from what I'm saying, you could always read about it. But what the MAE does is it looks at the points to the line, measures the distance between these points to the line. That is the learning curve now, or the learning line, or the learning pattern, whatever it is. It measures the distance between the points to the line. Then it does this for all of the points. Then it finds the mean of the distance of all of the points. when it gets the mean of the distance of all of the points, that is one of the ways you can measure how well the model is doing. So now imagine a line drawn, say, along this axis now, as of the graph. You expect a mean absolute error that will be a lot higher compared to this one. It will be the same if it's anywhere apart from here. This is a perfect fit to the model, so the MAE should be extremely low. The lower the MAE, now that is the mean absolute error of the model, the more the better, or the well-tuned the model is, that is, the model performs optimally. And then there's the MSE. The MSE is actually the square of an MAE. And what I mean by this is, you know what I said when I said the distance between the points and the line. Now that's how you measure the MAE. That is the same process that you measure the MSE, which is the mean squared error. You look at this distance. Just that whenever you get the distance between a point here and a line here, you square the value that you get from that distance. And then you do the same for this. It keeps doing like that for all of this. So the MSE is always higher than the MAE, although they are performing the same function. But why the MSE? The difference now between the MSE and the MAE, that's the mean absolute error and the mean squared error, is that the situations now where when you start testing out your model, say you know that when you first start with the model, you don't just go straight to fine-tuning the model directly, or you just say, okay, you choose the exact model you want to make it up. You just look at it and you're like, okay, the random forest regression. No, you don't just start that way. You start by roughly selecting models that, okay, this model should work, this one should work, based on how much you understand the model. So after looking at the understanding you have for the model, you say, okay, then you just roughly check out the accuracy. Now, the accuracy here is the mean absolute difference error from that model. Yeah, okay. There's a question here saying, can we say MAE is the mean of the difference between the actual and the predicted? Exactly. That's just the exact definition of an MAE. Is the mean of the difference between the actual and the predicted. Nothing more. So if I was extensive with what I was saying, I was just trying to build on your intuition, but that is the exact definition of the MAE. After selecting the model now, after selecting the model, let's say the first prediction you make with the MAE gives you a value as low as, say, between 2 to 5. Now, that shows that the model is actually performing optimally from the start. Now, if you want to fine-tune the model further to check how well you can perform, you switch from the MAE to the MSE, because the error that will be generated by the MSE would be higher compared to the MAE. And the higher the error, the more you can attempt to see if you can reduce the value. That's the generalization error that comes when the model is when you are fine-tuning the model. Okay, so not to make too much of it for you on that. Okay, let me expand more on this. So the way we split the data set now, scikit-learn is very easy. Just say from FTA-learn, which stands for scikit-learn, model selection, import the train, then underscore split. Now, this is the exact function responsible for splitting your data sets into the training and the testing set. Now, our data sets as it is right now isn't really processed. If I call the data set, that's the big math. The data set. Realize that most of the value are entity encoded and just raw. So what I did before this course was I created a Python script. So I created a Python script that would prepare the data set for us. Since I can't really, as I said, I don't want to interfere with what we have going in the main here, and I want us to like perform all our evaluation and testing here. So this Python script here will be handling the preparation of the data set. And I remember that I gave you guys a task on creating something that will actually do that. So I won't really be doing it. I won't be revealing the code to you guys. So done with the equation type, I don't start with classification type, but I'll just quickly import it from here. So I'll just say, what's the name of the function? The name of the function is prepare the data set. Prepare the data set. So I'll say from this math import. This is the function that I'll prepare our data set. So I'll just pass the data set directly into that function. So I'll just say prepare next data set. So if I call this particular method in the next method, we say that everything has been converted now. The whole value in the data set has been uploaded, and we are ready to receive it. Selecting the model and performing various things like the validation and all of this stuff. So first thing we want to do now, we want to split the data sets. We want to first, before we split the data sets, the first thing we need to do is separate the item outlet field, which is a target. We want to separate that. I'll just call the target variable the target column. I'll call it the target column. Name of the variable is the item outlet sales. So that's the target column. So I'll start by saying, okay, our target now, which is okay, our target now, the data, the series rather, that's our main data set. Our main data set, target column. So just to produce our set targets, but in the series, we just do something like this. So we know that our target is working pretty well. This is our target. So for the rest of the data, we get making use of the drop statement, but not making use. We'll make use of the drop method. Make use of the drop method, but we won't make our changes in place. And what I mean by this is to say, okay, the big math sales, which is the name of the data frame, drop. We're dropping the target column. Dropping the target column. And we're dropping it from the column axis. That's going to be equal to 1. Equal to 1. So that's for the data. Now if I ask for the data, what we realize is we still have this, the values of the other system, but the item outlet sales are being removed now from this. So we have our data and we have our targets. We can now proceed to doing the main thing, that is splitting the data set. So I just asked for what is the train test split, which is a function. Now looking at the function, it says it splits array or matrix into random train and test subsets. And what that means is that, okay, it takes your data set now, which has been provided here as arrays, and it splits it into the training and the testing set based on how you want that to be done. So just to, there's always an example in every scikit-learn documentation, which you can always preview at the lower area of how this can be done, so that you can always split, you can split the X and Y here, which represents the data and the targets. And I believe you could also split a single value. That if you wanted to split only, if the data set was combined now, that is both the X values and the Y values they combined. You just pass that into the data set and it will still split it evenly without separating the data. But just to move along, I'll copy this, just to save time, I'll copy the variables that I'll be making use of now, which is the X string representing the data, the training data we'll use. That is the training features we use when evaluating the data, training the model. And this will be the training targets. While this will be the test features and the test targets that we'll be making use of for the, when we split data set. So I guess X string, X test, Y and Y test.
No, please excuse me.
Yeah.
Please, can you explain the X string, X test, Y string, Y test again? I didn't really hear it.
Okay, let me explain. It. So when you shall got most of what I was saying about the need for having a training and a testing set. So what the X string represents our training set now, and the X here represents the futures, which this X is going to be the training futures of the data set. So it's going to take this data now, which represent the futures, that's excluding the item outstets sales from the data. It's going to take this futures, it's going to split it alongside the target and give a specific proportion of training value, that is the training futures now to the X string. That X, the values that the data that is going to be given to training futures X underscore train is what we'll use to train the model, while the X test is what we'll use to check if the model actually learned what it was trained on. I don't know if you get it better now, or should I explain?
I didn't really get to.
Okay. Let me try and explain it this way. So our own data set now consists of about 8,523 points, right? So what we are trying to do is we want to split the data into two. We'll use one point to train the data. We'll use another point to test the, we'll use one point to train the model rather. Then we'll use another point to test the model. Now, the point that we want to make use of to train the model is what we call the X string. It represents the futures of the model that will be extracted from the data sets to test the model, while the X test represents the futures of the model that will be used for evaluating if the model is actually generalized to new instances. You get it better now?
Yes.
Okay. So the train test split now, we
what about white train and white test?
Okay, the white train stands for, it's just like the X train. The white train stands for the targets, unlike the this thing now, that is the futures, the X input values. The white train stands for the outcome. So when we say, okay, you know that a model takes a model takes the training values, then it predicts the outcome. When we train now, what we do is we take the training value, and we take the training value and we predict what's the value of y, which is the target value during training process. Then when we want to test, that's when we want to perform an evaluation, we take the y test, which is the target value, and we place it directly, and we use the target value now to, so we use the testing variable now to make predictions, which will be evaluated on the target value, the test values, y test. It's just like, okay, when we train the model, we train it making use of the data, that is the input features and the target. So when you say, okay, you have been given X and you have been given Y, use X to find Y. That is, use this X to find this Y. Once the model have been able to successfully use this X to understand how the value of this Y is gotten, we now give it this X, which is the testing value. This particular X test now, he hasn't seen the data point at all. He hasn't seen it before. Now, when he sees this value, he makes prediction based on what he has learned from this value X text and this value XY. Now, when he makes that prediction, the prediction is what we now will make use of to evaluate the unseen data. That is the newly generated, and that's the predictions that the model makes is what we use to evaluate on the actual values, the actual data points. But the thing is, if you don't get it now, you should get it later. So maybe I should just proceed for now.
Yes, please proceed.
So given the data and the target, we need to provide something called the test size. And what the test size is what the test size is that it takes the what it acts like the volume of data that should be made use of for testing. And one of the ways I usually calculate this is I make use of the overall size of the data. So that's 8553. So that is this 8,503 represents the bulk of the data. That is the amount of rows present in the data. And multiplied by the fraction, say 0.2, which represents 20%. This will give us how many data will be used for testing. So if we were to make use of 0.2, that's 20%, we have 1,704 data points for testing and evaluation. So I would actually leave this because I still want to create something called a validation set. And as I said, you guys will still get it as we proceed along. So let me just quickly create the test sets. Now we have a point. So that we have about 1,704 values for the X test and the XY. And then I just set the random states. Not as necessary actually, but I love being as explicit as possible. So that's for the X test. So let's just confirm if what we did actually worked. I'll just copy this to here. But we want to ask for the shape of the value. The shape of the value will give us the amount of value that actually is for training and testing. So we will be training with about 6,818 data points and testing with 1,705 data points. So just to quickly give you guys a preview of what I've been talking about with the training set and the testing set, I'll just quickly create a model, not something solid. I'll make use of the linear regression model because it should work. So I'll say from dot linear model to import linear regression, which is the linear regression model. So I'll just call it the linear. But that's one of the common terminologies to name a linear regression model. So linear regression. that is just a simple linear regression model. So I'd say the linear dot fit. And now what I'm trying to say is, okay, make use of this X string, make use of X string and Y string, learn the data. So when I pass it this X string and Y string, what it does, just like as I explained when I was talking about the encoding, the label encoding, ordinary encoding, and the like, it takes X string as the input, takes Y string as the output, and learns the relationship between the input and the output. It takes a little while to learn it. It's not actually a huge data set, so we see that it's very fast. Then we now ask for the prediction. Now we ask it that now that you've learned prediction, now that you've learned the relationship between the input and the output, try finding, try seeing if you can predict what you've learned on your own. So that's it. We now ask the linear dot predict. The linear dot predict. So we'll ask it to predict that the X test now. The S test is now the data point that it is testing with. So we'll say, make your predictions. Now, finally, it has made its predictions. So one of the ways we can now check if the prediction, because now this is the predictions that the model made, and this is the actual value that we know to be correct. All right, this is what the model made. This is what we know to be correct. So we now want to evaluate how well the model did. We do that by making use of one of the metrics, and we'll be making use of the mean absolute error metric now. So that will be from dot metrics import. The name of the metric is mean absolute error. So that's the name of the metric, and the mean absolute error takes two values. It takes the actual prediction, which is called Y2, and it takes the predicted value, which is the Y3. So the actual prediction here is now the Y test. The Y test represents the values that are actually true. Then we now say, okay, given the actual prediction, what's the test prediction? The model prediction rather. So that would be prediction. So it says the mean absolute error between these two now is 854, approximately 854. This is how you can call it how well or how badly the model is performing, because it is making use of the difference. Now, what I try to explain from this diagram, it is checking the distance between the line that the linear model generated. It is making use of the line that the linear model generated, and it is calculating the distance between that point to that line. So from here, what our model is doing is given that distance, we can say our model is not actually performing that well, because the distance between the mean of all of those points, which are about the testing points, about 1,705. The distance between all, the mean distance between all of these points is 864. That's the model performance now. That's for the regression task. So the lady who was asking the question, what's the training data is, the test data and the likes, I hope you are clear on it now.
Yeah, so but my question is now, why is this mean absolute error value so large?
Guys, because
how do you not interpret it?
The mean absolute error just tries to give us, okay, the thing is this, the session will soon be over, so maybe I'll answer the question in the next session.
Okay, thank you.
Yeah.